All right, so good morning, everybody. So this week's video is going to be going over your quizzes from last week. Now, the quizzes from last week, if you still haven't submitted it, you still have time. I'm not going to mark any points down for quizzes that are submitted in quote unquote late. But the biggest thing about these quizzes is that you know where you stand with some of these material. Some of the material was review from before we left from this quarantine that we're currently in, but some of it was also pretty recent. So I wanted to give you a quiz because I wanted you to see where you stood. So you should all be able to see your grades by now. I know there's still a few, as you can see right here, that I still need to grade. But for the most part, if you have submitted your quiz, I have graded. So I want to go over the answers with you all. So here is a copy of the quiz. Now, what I'm going to do is I'm going to kind of mark around on this. And if you have questions after this video, please message me on Schoology. I want to be here for you. I want to give you the ability to figure these things out because some of the stuff is pretty tricky. So I want to be here for you when dealing and trying to figure out all of this material. So if we look at number one, when dealing with magnetic forces, it works just like gravity. The larger the magnet, the larger the magnetic force. The answer is false. So, as you remember, when we were dealing with magnets, we used small neodymium magnets, and those actually had a stronger magnetic force than a ceramic magnet. So, your goal was to change this sentence to make it correct. So, magnets actually don't work like gravity. Depending on how big or small the magnet is, does not actually necessarily correlate with the amount of magnetic force. It depends on how much magnetic material is actually in the magnet. All right. And then we go here, number two. Whenever we cut a magnet in half, you will have one south magnet, one north magnet. The answer is, again, false. Remember, one of those statements that comes with magnets is that they always have two poles. So if you cut a magnet in half, you just get two smaller magnets. There will be a north and a south pole on that magnet. Then we're looking at number three. Magnetic force and gravitational force are similar. Both forces are considered at a distance force, which means true. So what that means is, remember, in order for magnetic force or gravitational force to affect an object, they do not need to be touching. So remember, if you jump off Earth will pull you back down, even though you're not touching it. Magnets, they can repel or attract each other without having to touch one another. All right, number four, in order to increase an object's gravitational potential energy, you need to increase the speed of the object. Now, there's two things I want you to pay attention to. The one here is speed and potential energy. I got a few questions about this problem here. Remember, potential energy. The object should not be moving. And if we're talking about speed, potential and speed don't quite go together. So this one is also false. If you want to increase an object's gravitational potential energy, you need to bring it up off of the Earth's surface, or we just need to increase the mass. In other words, make that object bigger or add masses to it. But those are the two ways that you increase gravitational potential energy. You just bring it up off the Earth's surface and hold it up there, or you just make the object bigger. Now, here, let's look at number five. There was also a bunch of different answers I got for this one. So these diagrams, remember, you had to find the one that is incorrect. So a lot of people were looking here at a lot of people said A. Now, if we look, the magnetic force goes from north to south. That is still correct. Could this use a lot more arrows? Probably yes. Is it missing some? Yes. Is it as detailed? No. But the original idea of magnetic force is still currently correct. Then we look over here at B. We then have magnetic arrows going away north, which is correct, but then all eventually curving back to the south. So B is correct. C, however, is the one that is incorrect. So I want you to pay attention to look here. So if we zoom in on this a little closer, you can see that it has the magnetic force traveling from the South Pole to the North Pole, and we know that is incorrect. Magnetic forces always go from the North Pole to the South Pole. So this one was a little trickier. You had to really look at the details of each one of these three diagrams. But if you look closely, they all still have the same basic shape. However, it's the direction that the force is traveling, and we know that is always from north to south. Always. All right, so we look down here at number six. List two ideas that are true about all magnets. I got a variety of different answers. You could say that magnets attract and repel each other. They all have two poles. The like poles, north and north, or south and south will repel. Opposite poles will attract, north and south. Those will attract one another. So there was a bunch of different answers you could have put for this one here, number six. you basically just had to give me two responses that were true about all magnets. Now, if we look down below, we keep going. This one here was tricky. I know that there wasn't a lot of information on this problem, and my goal was in this case to make you think. Now, I accepted actually a variety of different answers for this one, so I want to take a look at what this problem is looking at. So remember, you're looking at gravitational potential energy. And the two ways to increase gravitational potential energy, remember, number one, bringing the object off the ground. Number two, increasing the mass of it. Now, in this problem here, you don't have a lot of information. There's actually a lot of information missing, but you can get the basics of this diagram by looking at it here. So looking here, we have two balls. One of the balls up here is much larger than the other one. And then we have object A, which is the larger one, sitting at a lower elevation. So if we look, B and C currently have more gravitational potential energy than A. Now, some of you said that object A had more gravitational potential energy than object B. I accepted that answer because we don't know their masses. If we knew their masses, we'd actually be able to get a little more of a detailed answer. But what I was trying to make you do is I wanted you to think, because this problem will leave you thinking if you're not quite sure. So if you said the lowest one was A, I accepted that. You also could say, and some of you did make the argument, that the lowest one was also B, because you knew that the higher the mass object, the greater the gravitational potential energy. So I accepted A or B for both of these responses. But the one that has to be absolutely correct is the one that most gravitational potential energy is C. So if you place these in like BAC as your order or ABC, I accepted it. If you, however, dealt with putting object A over here as the one with the highest gravitational potential energy, that is where you started to lose points. So if your order was something different than A, B, C, or BAC, that's where I started taking off points. So remember, this is not an easy problem. There's still a lot of information missing. We don't know the heights per se. We also don't know the masses. So, but I wanted to make you think on this one. And so remember, gravitational potential energy increases it by either bringing the object up in the air or, in this case, increasing the mass. All right, so let's look here at number 10. So number 10 deals with, you'll see, actually, if you watch the video in the first assignment for this week, it shows you how this is possible. So when we saw static electricity interact with the water, what was happening between the friction tool and the water? Now, in this case, the water was attracted to the friction tool. Why is that? Because on the friction tool, what we had here, this is the friction tool, we had a bunch of static electricity. So a bunch of electrons were gathered up on the plastic tool. And when the water was falling, it actually would bend its way towards the friction tool because the water has a positive charge. And we know that opposites will always attract. So in this case here, with the opposites attracting, remember, it's the friction tool is gaining negative electrons. It's not that it's gaining, and it's not the water has positive electrons. The water just has a positive charge overall, just a positive charge. It doesn't mean that it has positive electrons. It just means it has positive charge. This friction tool had a negative charge because it gained a bunch of electrons. So the water in this case was attracted to it. So I would watch the video I put up in the week 2 online folder in the first assignment for the week. That will help explain and show this more. Now, here we have our copper pipe and magnet scenarios. This is what we saw in class twice, actually, and you made 2 models based on this. So this question here is to make sure that you fully remembered this one. Remember, so we had our copper pipe, and then we dropped a magnet through it. And by dropping a magnet through it, remember, magnets themselves are surrounded by a bunch of swirling electrons. Remember, we can't see them because they're super, super small, but this magnet was surrounded by electrons. And what copper loves to do is copper conducts electricity, and electricity is all made up of electrons. So when this magnet fell through the copper pipe, the electrons were able to travel through the copper pipe. And one of the telltale signs of a magnet is that it's surrounded by electrons. So if we allowed something to surround itself with a bunch of electrons, which the copper pipe did, it created a magnetic field on the inside of the copper pipe that helped repel the magnetic field of the magnet itself. So there was two magnetic fields. One from the magnet, and the other one was inside the copper pipe. All right, last but not least, the last problem here is you have this screw that was surrounded by a wire. And what did we need? We needed a battery. So here's my wonderful, beautiful drawing of a battery. And here we're going to connect those wires to the battery, connect and connect. And what happens is when you connect this battery, all of a sudden, electrons start to flow through the wires. So remember, electricity is all electrons. So we have all these electrons that are flowing through the wire, and then all of a sudden they now surround our screw. So we have tons and tons and tons of electrons surrounding the screw. Even though the screw was not magnetic to begin with, when we surrounded it with electrons, it turned into a temporary magnet. So you have a bunch of electrons surrounding this thing, a bunch of negative charges, and you essentially made an electromagnet. Remember, the screw to begin with was not a magnet, was not even magnetic. However, when you surround something with electrons and it's metal, you can turn it into a magnet. It becomes an electromagnet. Same thing here that happened with the copper pipe. It wasn't magnetic, but when you surround it with electrons, it turned into a magnet, and it had a magnetic field. So with this one here, we needed a battery, we needed a power source. Those electrons surrounded it there and turned it into a magnet. So hopefully this offers some clarity after going over the quiz itself. That was the goal of this video. Remember, if you have questions, please submit them on Schoology. I want to be here for you guys during this time. I know it's different with us not being in class and everything like that, and this is a little more, I guess not really what you're used to seeing, but hopefully this helped add some clarity when you see your quiz grade itself as to what maybe you scored on the assignment and what maybe you may have made a mistake on. So thanks, and hopefully you enjoyed the video.